end of the second month of our IUCAA Colloquium on Thursdays, and we very nicely transitioned to Zoom, and I'm tempted to keep it like this for a long time. 4 p.m. And today I'm very, very happy to welcome Professor Sriramkumar to our colloquium. He's of course a familiar face to all of you. Sriram did his PhD here under Professor Padmanabhan at IUCAA. When I first joined IUCAA, Sriram was here as a student. Then he went off to do a postdoc with two postdocs abroad with very illustrious people, because he worked with Bekenstein in Israel, and then went to Alberta in Canada, and then came back as a faculty member at the HRI in Allahabad, and then joined IIT Madras, went back to where he did his master's. And in IIT Madras, he's now a professor. He, until very recently, was also the secretary of the IAGRG. So we are really excited to welcome him back. I'm very sorry to the audience for our initial hiccup. I think we will now be smooth for the rest of the talk, and then at the end, we will follow our usual way of taking questions, when people can ask questions by raising a hand using the Zoom alternative, the Zoom option. Okay, up to you, Sriram.
Thank you very much, Shomak. I should begin by thanking Shomak Kandu and IUCAA for this invitation to give this colloquium. I was hoping to be there, spend some time this summer. Unfortunately, it couldn't happen. I hope to come back again maybe next summer. Inflation is a remarkable paradigm. It is simple and it is efficient. This simplicity and efficiency has also led to a situation where many models of inflation remain consistent with the data. This has led to even the concern whether inflation as a pattern. It seems important, even imperative, to explore alternative scenarios for the generation of the primordial perturbations. It would be fair to say that the bouncing scenarios are the second most popular mechanism for the generation of mechanism for the generation of perturbations. These corresponds to a situation, these scenarios correspond to situations wherein the universe contracts, goes through a contracting phase. The scale factor reaches a minimum before the universe begins to expand. One doesn't have a big bang. The scale factor remains finite but non-zero, and before it begins to expand. I mentioned as to how it is easy to construct inflationary models. In complete contrast, it is fairly non-trivial, even challenging, to construct well-motivated bouncing models. And importantly, models which are consistent with the data, viable bouncing scenarios. In this talk, after an introduction to inflation, where I will highlight those aspects of inflation which I shall require to compare and contrast with the bouncing scenarios later, I will go on to describe some of the results that I have obtained along with my students over the past few years in the context of bouncing scenarios. Here's an outline of my talk. As I mentioned, I will start with some remarks on inflation. I will highlight a few key aspects, and I will illustrate as to how it is quite consistent with the data. What are the models that are consistent with the data? And then I will go on to elaborate a bit on what I said about bouncing scenarios. And I will highlight some of the key aspects. Then I will go on to discuss a specific model we have constructed, where we arrive at scalar and tensor power spectra, which are consistent with the data. In fact, this first model that I will describe, which leads to something called the Matterbound scenario, leads to strictly scale invariant spectra. What one finds is that it is easier to discuss the evolution of tensor perturbations. It's more challenging to discuss the evolution of scalar perturbations. So I will first discuss the tensor perturbation and then go on to discuss the scalar perturbations, how the tensor to scalar ratio, can be consistent with the data in such scenarios. The reason as to why the tensor to scalar ratio has to be consistent, in particular small in these bouncing scenarios, will become clear when I discuss the behavior of the scalar and tensor perturbation during the contracting phase in a Matterbound. Then I will go on to discuss how to generate the spectral tilt so that the scalar spectral tilt is consistent with the CMB constraints, namely NS is 0.96. And something very interesting, whether bouncing scenarios can lead to features in the primordial spectrum. It is fairly easy to generate features in the inflationary primordial spectrum. You would have heard about a lot of work in the last 1 or 2 years, how to enhance power on small scales to lead to larger formation of primordial black holes, for instance. I will discuss the generation of spectral features in bouncing scenarios. It turns out to be a lot more complicated to model in the context of bounces. Time permitting, I will talk about the 3-point function. It is easy to discuss the tensor by spectrum, and then I'll close with a summary and outlook. This talk is based on the work I have done with my students, Devika Chaudhary, Srinath, and more importantly, this is most of the work I'm discussing here. I've gone into Ratul's thesis, Ratulnath Ravindran, who was a graduate student at Math Science, who's currently a postdoc and so on. Let me, as I said, start by making some remarks about inflation. Why do we need inflation? Well, you need inflation to overcome horizon problem. And what is the horizon problem? Tropies in the CMB. And the white patches I have drawn on top of these CMB anisotropies represent the size of the causally connected regions in the CMB sky within the hot Big Bang model. That is a scenario without inflation. In other words, the causally connected patch in the sky is just about a degree or so. However, we know very well that even widely separated regions in the CMB have virtually the same temperature. In fact, the deviation in uniformity is about 1 part in 10 power 5. This is the statement of the horizon problem. Why are different patches in the CMB sky have the same temperature? There is another way of stating this horizon problem, and this is illustrated on the left side. On the left, the figure on the left side here, the y-axis is the so-called conformal time coordinate, and the x-axis is the linear spatial dimension. And evidently, in conformal time, light cones are at 45 degrees in a Friedman-Robertson Walker universe. This red patch is where the CMB originates from. It is the last scattering surface. You have a backward light cone in green, and invert this blue light cones that I illustrated on either side here, and you will have a forward light cone. What one finds is that within the hot Big Bang model, you have a radiation-dominated epoch here, and you have a largely matter-dominated epoch here. The backward light cone is much larger than the forward light cone, and that's why you see these different patches in the sky which are not causally connected. But then how do you explain the CMB sky? Well, it is fairly straightforward. In radiation-dominated universe and matter-dominated universe, the Big Bang corresponds to eta equal to 0, the conformal time eta equal to 0. If I can make eta negative, I'm done. I can push eta behind, Big Bang behind considerably, and I can ensure that the forward light cone is as big as the backward light cone. And that is what inflation does. It allows you to have an epoch wherein eta is negative. It pushes Big Bang behind, and you have an epoch where the forward light cone grows adequately to ensure that it is at least as big as the backward light cone. There is yet another way of understanding the horizon problem. This figure contains 2 curves, one in blue and one in red. The curve in blue represents the physical wavelength. It is always proportional to the scale factor. We have a log-log plot here. The x-axis is logarithm of the scale factor, which is often referred to as e-folds. And the red lines here correspond to the Hubble radius during the radiation-dominated epoch and the inflationary epoch. Clearly, if you don't have an epoch of inflation, if you have only radiation domination, all the modes of cosmological interest would have been outside the Hubble radius at a suitably early time. However, if you have an epoch of accelerated expansion, you can ensure that the mode, even the largest mode today, comes inside the Hubble radius, as you can see, this blue line coming inside the red line at a suitably early time. And one can show that if you have an epoch of inflation lasting at least 65 epochs or so, and I should emphasize that this duration of inflation is often counted, from the end of inflation. So you start here, and if you have 65 epochs or so, you can ensure that the largest scale today, corresponding to the Hubble scale today, can be inside the Hubble radius. And what do you do? Once they are inside the Hubble radius, you can impose well-motivated initial conditions and evolve these perturbations to see their imprints, to evaluate eventually the corresponding imprints on the CMB. And you need an epoch of accelerated expansion, which is what inflation is. And it cannot be achieved with the aid of matter or radiation. You need to turn to other exotic sources to drive inflation. And the exotic source one turns to is a scalar field. And one can work with a simple canonical scalar field. And there are many models, many potentials. These canonical scalar fields are essentially described by various potentials. You can have a variety of so-called large field models where inflation occurs when phi is much greater than MPL, or small field models where phi is much less than MPL. Or you can have more complicated models called hybrid models where you can have more than one scalar field. And many of these potentials will easily admit inflation. And in fact, you can have adequate duration of inflation of 60 or 65 epochs or so. But there are many, many such models of inflation. This is a list. This is somewhat old, almost 2 decades old. There is a more updated list which has been compared with the data. And I will not show the list. I will illustrate its performance as we go along. So there are many models of inflation, and one would like to sort of, rule as many of them as possible. And we turn to understand the nature and the shape and the form of the perturbations in this context. And as you may know, the perturbations can be classified into 2 types. The first is the primary one, which are the scalar perturbations, which are responsible for the density perturbations. And we will always have tensor perturbations, even in the absence of sources. And these scalar and tensor perturbations are described by these actions at the quadratic level. R is the curvature perturbation, and gamma ij are the tensor, traceless transverse tensor perturbation. And I should clarify why R is referred to as the curvature perturbation. Remember, we are working, in a spatially flat Friedmann universe, or even if it doesn't start with a spatially flat Friedmann universe, inflation quickly drives the universe towards flatness. Inflation, apart from solving the horizon problem, it also alleviates the flatness problem. And this curvature perturbation reflects the extent of deviation from the spatially flat situation. And this is what is responsible for the density perturbations. You can vary these equations and look at the Fourier modes, and they are governed by these equations that are written down here. And you may wonder where the notion of the potential goes in, and that is buried in this quantity called Z, which is proportional to the scale factor, and this epsilon1, which is the first low rule parameter. The potential determines the form of A and epsilon1. That determines Z, and that in turn determines the behavior of the curvature perturbation and eventually the perturbation spectrum. In contrast, H, the tensor perturbation, depends only on the scale factor. How do these perturbations behave? Well, as I mentioned, you impose these initial conditions we have seen earlier. We have logarithm of the Hubble radius and the wavelength of the perturbations plotted against logarithm of the scale factor, which is E4. You impose the initial conditions when they are well inside. You evolve them onto super Hubble scales and evaluate the perturbation spectrum on super Hubble scales. How do these perturbations behave? Well, when they are inside the Hubble radius, what you essentially have is that the wavelength of the perturbation is much smaller than the curvature of the universe, so to say, and therefore it doesn't see the curvature at all. It behaves as though it is in some sense Minkowski spacetime. And Minkowski spacetime, the modes of the quantum fields oscillate, and that is what happens on the left-hand side of this figure here. What has been plotted are the real and the imaginary parts of the curvature perturbation. It has been plotted as a function of time, and what you should understand that the modes leave the Hubble radius at, this particular mode leaves the Hubble radius at the E fold of n equal to 18. So to the left of n equal to 18, you have the sub-Hubble domain. On n greater than 18, the modes are on super-Hubble scales. So the modes oscillate in the sub-Hubble domain, and as soon as they leave the Hubble radius, they quickly freeze, and you can evaluate the spectrum immediately after. And this particular feature happens to be very convenient because you can, particularly when you want to solve these modes numerically, because you can impose the initial condition when the modes are slightly inside the Hubble radius and evaluate their amplitude on super immediately after they leave the Hubble radius, and thereby arrive at the primordial spectrum. In most of the models of inflation, the so-called slow roll models, you can characterize the primordial spectra, the scalar and tensor perturbation spectra, in this simple way. You have 4 parameters that appear here. The quantity K star is a pivot scale at which we know the scalar perturbation amplitude of the scalar perturbation normalized. The Kobe amplitude of about 2 times 10 power minus 9 or so. What we are primarily interested then is the quantity Ns, At, and Nt. Since we seem to be far from seeing the imprints of the primordial tensor modes, our primary goal is to understand what is At. Therefore, what we are interested in Ns and At, actually, we don't look at At, we trade off At for something called the tensor to scalar ratio R, which is formally defined as the ratio of the tensor amplitude to the scalar amplitude, or At by As. So what one is interested in constraining are R and Ns, and you would have seen this picture where we have the constraints from the CMB and other data on the tensor to scalar ratio on the y-axis and the spectral tilt Ns on the x-axis. And what one finds is that some of the originally popular models, large field models like the quadratic potential and the lambda 5-4 model, are increasingly inconsistent with the data, primarily for the reason that the tensor to scalar ratio is being constrained more and more strongly. The current limits indicate that R is less than 0.06 or so. So something like the m squared phi squared model and the lambda 5-4 model is well out. The m squared phi squared model is beginning to be out. Even the linear potential is out. And one of the models that fits the data extremely well is something known as the Sriramkumar model, which in fact was the original proposal for inflation, which was achieved with the R plus R squared term to describe gravity, which can effectively be written as R plus a canonical scalar field described by a specific potential. This particular model leads to a scalar spectral tilt of about 0.96 or so, and an R of 10 power minus 3 or so, and it fits the data exceptionally well. I had mentioned that there are many models, of inflation which can be consistent with the data. One of the challenges one finds is that, in this blue are models which it is difficult to rule out, okay? Which can be, something can be said upon these things in blue. The things in red, green, and light green are models which are, these can be strongly ruled out, to some extent moderately, and these cannot be ruled out very well. And one finds that there are many, many models, despite the considerable effort by Jerome Martin and co-workers to, carry out a systematic analysis of various inflationary models with the data. One finds that, many models can be consistent with the inflationary models, can be consistent with the data. However, the data seems to favor a certain type of models, the so-called plateau inflation, of which the most popular, as I mentioned already, is the so-called Sriramkumar model. That is the situation as far as inflation is concerned. Now, I should emphasize, apart from constraints on the power spectra, there are constraints on non-Gaussianities as well, but I'm afraid I may not have adequate time to cover non-Gaussianities. If there are questions or concerns about non-Gaussianities, I will respond to them at the end of the talk, and now I will proceed to bounces. I'm sorry, it hasn't gone further. Apologies. So, what are bouncing scenarios? I had briefly mentioned earlier that they correspond to a situation where the universe initially goes through a period of contraction until the scale factor reaches some minimal value before it begins to expand. They horizon problem I have illustrated as to how you can overcome the horizon problem in inflation And I have also illustrated as to how you can impose well-motivated Minkowski-like initial conditions on the perturbations, in the context of inflation. You can do similar things in the context of bounds during the very early times during the contracting phase. Under certain conditions, we will see, in complete contrast to inflation, if you have a non-accelerated contraction, you can impose such Minkowski-like initial conditions. However, there is an issue. Matter fields, we will see, will have to violate the null energy condition near the bounds in order to give rise to scale factors that lead to the bounds. And of course, there are genuine concerns whether such an assumption about the scale factor is valid in a domain where near the bounds general relativity is supposed to fail and quantum gravitational effects are expected to take over. We will focus on classical bounces by ensuring that the energy density of the total fields in the universe never, cross and never approach densities correspond to Planckian densities. So this is a typical behavior of the Hubble radius and the wavelength of the perturbations in a bouncing scenario. This bouncing scenario is called, what we are focused on is a matter bounce. In contrast to E-fold that I had introduced earlier to describe, time during inflation, I work with a slightly different parameter. Instead of ordinary n, I have script n. The reason being, A, the scale factor is e power n, n being the E-fold in the context of inflation that describes a monotonically increasing, it's a monotonically behaving function. In contrast, the scale factor decreases and increases, and therefore E-fold is not a very convenient variable to describe bounces. We work with something slightly different, which is, we call it En-folds. And in this talk, for most part, we'll focus on a certain class of bounces which are called symmetric bounces. We will write A of eta in terms of eta being the conformal time coordinate, which will turn out to be symmetric in eta, or equivalently in terms of the script n, we have a function which is symmetric in n. We work with A of n, which is En squared by 2, and we call the script n, you will see, we refer to as the En-fold, and that will be our time variable for most of the time. So what has been plotted, as I had done in the context of inflation, I have plotted the Hubble radius in red and the wavelength of the perturbation in blue. And I should point out that right at the bounds, at n equal to 0, the bounds corresponds to where the scale factor is a minimum. Therefore, A dot or A prime will vanish. And since the Hubble radius is H inverse, there will be a 1 over A dot or 1 over A prime. And that will lead to a divergence of the Hubble radius at the bound. That's what this spike indicates. It's proportional to the scale factor that is well behaved, as illustrated in blue. And this corresponds to a scenario where you have what is referred to as a matter bounce. That is, at very early times, you have, the universe contracts as though it is dominated by matter. In other words, A will be proportional to eta squared, as we will see. What one can show, this is something I mentioned a few minutes earlier, one can show that if you have a non-accelerated contraction, remember, in the context of inflation, you want accelerated expansion in order to ensure that this blue curve, that is the wavelength of the perturbation, is less than the Hubble radius. In complete contrast, you require non-accelerated contraction at very early times if you want the modes to be inside the Hubble radius in a bouncing scenario. Now, what kind of scale factors does one work with? Well, we will focus on scale factors of the following type. This is a choice we have made. As we will see, it allows us to solve for the background and the modes completely. We shall work with scale factor of the following form, where A of eta is essentially A naught 1 plus eta squared by eta naught squared. There is a 1 plus epsilon in due course. Notice when epsilon equal to 0 at very early times, A of eta, that is eta going to minus infinity, A of eta behaves as eta squared, which corresponds to a matter-dominated epoch. And you can ask what kind of sources can lead to such bounces. One can, again, make use of the Friedman equation to construct the corresponding energy density, one finds that, if you have two fluids, with a certain equations of state, then you can achieve a scale factor of this type. And these two fluids, their dependence on the scale factor are as follows. Rho, let us again, as I said, focus on the epsilon equal to 0 term, which I shall hereafter refer to as the matter bounds. Rho 1 will evidently, when epsilon equal to 0, will behave as 1 over a cubed, and rho 2 will behave as 1 over a power 4. In other words, if I have matter and radiation, I will be able to achieve a scale factor of this form. But there is a caveat here. Notice there is a minus sign here. In other words, I need something which behaves like radiation, but with an energy density that is negative. And we will model, we will eventually need to model this in terms of scalar fields in order to understand the evolution of the perturbations, how they originate, how they evolve, etc. And what is the power spectrum. This negative radiation with negative energy density, I have to turn to Gauss fields to achieve these bounces. And this is one of the major drawbacks of the models we have focused on. But I should emphasize, this allows us, this particular modeling allows us to evolve the perturbation and study many aspects we need to study. So we have these two fluids, okay, and we have the scale factor. As I said, we focus on first focus on the case where epsilon equal to 0, which we shall refer to as a matter bounds. Why am I interested in these matter bounds? Okay, before I discuss that point, let me just make a couple of remarks. I had mentioned earlier as to how I can work with parameters such that I can avoid taking into account the quantum gravitational effects. What has been plotted on the left is the quantity h dot in a suitable dimensionless way. On the right, I have plotted the total energy density in the universe. In fact, I have plotted rho by MPL power 4. There are a few points that I need to emphasize with the help of these figures. Notice h dot turns positive around the bounds. In fact, h dot, it is not very clear from this plot, but you have to take my word for it. H dot is negative here, far away from the bounds, on either side, in fact, both prior and after the bounds, and it turns positive close to the bounds. And this is where it violates the so-called weak energy condition. I have written one of the Friedman equations here. If h dot has to be positive, evidently rho plus p has to be negative. And this is where, why we require this kind of Gauss fields in order to achieve a scale factor of the type I illustrated earlier. So firstly, h dot turns from negative values, it turns to positive close to the bounds. It crosses h dot equal to 0. And this poses some challenges when we evolve the curvature perturbation, as I will describe later. On the right, I have plotted the so-called the total matter density, the sum of all the matter in the universe, both radiation and matter in this context. Okay, and I plotted rho by MPL power 4, and it's evidently symmetric about the bounds. And another point to note is that h vanishes at the bounds, the Hubble parameter, and therefore the total energy density also vanishes at the bounds. But notice what is the maximum value of 4? It is like 10 power from the quantum gravitational regime, and therefore bounds remains classical. I had said I will clarify as to why we need to focus on the so-called Matterbound scenario, and that can be illustrated by examining the so-called Mukhanov-Sasaki equation that describes a tensor perturbation. And that is given by this equation. Remember, h is my tensor amplitude. I had written the equation of motion when I had discussed inflation. And a is the scale factor. The Mukhanov-Sasaki variable is essentially a times h, the tensor amplitude. And one can show that it satisfies an equation of this type. For instance, if it is in d zeta, it's just 2 by eta squared. And I should also emphasize that the tensor spectrum hk is uk by a depends only on time. All the k dependence is carried in uk. Therefore, if I have two different scale factors A that lead to the same UK, you can expect them to lead to the same power spectrum. And you can ask under what condition that happens, that is where the equation for UK remains unchanged. One finds that if I have as given by this expression here, then you can show that UK remains unchanged. In other words, in both these cases, A double prime by A or equivalently A tilde double prime by A tilde are the same. And in the case of d zeta, recall A is 1 over eta. So there is a 1 over eta here. There is a 1 over eta squared, which goes in the numerator. So you have integral d eta eta squared, which is eta cubed. And eta cubed by eta is eta squared, which is matter domination. So in other words, the dual, so to say, to d zeta is a matter bounds. If I have A of eta, which behaves like eta squared, then I'm guaranteed to have a scale invariant spectrum. But I should emphasize that this is true only, if I have A behaving as eta squared at all times. In other words, during the contracting phase, you will have a scale invariant spectra, but you nevertheless has to evolve these perturbations across the bounds to show that they indeed, have the same scale invariant form post bounds as well. This is the challenge. So our goal is to construct, as I had mentioned earlier, a scalar field model that leads to the scale factor of the form, of the Matterbound's form that I had written down, and use this model to examine the behavior of the scalar and tensor perturbations. I had already mentioned as to how the tensor perturbations depend only on the scale factor A of eta. Since I have the scale factor A of eta, I can go on to first examine the behavior of the tensor perturbations in a Matterbounds. So what do I have? I have A of eta, which is given by this expression here. And K naught is the scale associated with the bounds. In fact, since we are writing in terms of eta, the actual scale that is associated with the bounds is K naught by A naught. And I had just shown as to how the Mukhanov-Sasaki variable corresponding to the tensor perturbation UK depends on A double prime by A. You can quickly calculate A double prime by A associated with this, and you obtain it to be open. And I have illustrated the behavior of A double prime by A here. I have constructed some suitable dimensionless quantity here, and here is my EN. It's like a quantum mechanical scattering problem, just as in the context of inflation. If you have a mode with a certain K, which corresponds to a certain energy, they will at very early times here they are in the sub-Hubble domain and they will oscillate, and as it crosses the potential here where it will continue in to infinity. Okay, so in contrast, in bounds it tapers off, and which are far removed the bound scale. I had already mentioned, or K by A naught are much smaller than this bound scale, which can be close to the Planck scale. So what it means is that the K squared, which corresponds to the energy in the scattering problem in quantum mechanics, is somewhere here much smaller than the P here. And the modes leave the
Oops, it seems like we are having connection problem.
Are you able to hear me reasonably uninterrupted? Okay, I'll restart the screen.
Yeah, thanks. Sure. We lost you for about a minute.
Yes, Kandu. I'm just trying to share the screen. Are you able to see me now? Okay, all right. How much time do I have, Kandu? 20 minutes?
You have about 20 minutes, yes.
Okay.
You have about 20 minutes. Go ahead.
Okay. Okay.
Yeah, we started a little late.
Let me start off. I'm sorry about that. My internet seems to have got disconnected. So I was describing as the behavior of this quantity A double prime by A, which determines the evolution of the tensor perturbations. So what happens is that the modes are on sub-Hubble scales. They reach the super Hubble domain, and then if you allow the bounds to continue in the same manner, okay, they will eventually re-enter the Hubble radius. But we will not do that. We will stop the evolution in this manner, evolution of this particular scale factor at some point of time, post bounds roughly corresponding to the epoch of reheating in the standard Big Bang model. So let me illustrate how the tensor perturbations evolve. I had earlier described the evolution of the perturbations in an inflationary scenario. They oscillate in sub-Hubble scales. That is what is happening here in the left regime here. The oscillations are not very evident because the amplitude of these oscillations are growing rapidly. And what is happening is that this amplitude grows. The dashed and the solid lines correspond to our numerical and analytical solution, which evidently match well. And what one finds is that as one approaches the bounds, the amplitude of the perturbation grows, okay, in contrast to inflation, where the amplitude of the perturbation comes down as inflation progresses. This is because of our contracting universe. They behave like a damped oscillator. They behave like a proper damped oscillator in the expanding universe. They behave like an anti-damped oscillator in a contracting universe, leading to an amplification of these modes. Once expansion sets in, when n crosses 0, you have these amplitudes freezing, at some value, and you can evaluate the perturbation spectrum post bounds at a particular scale. I had already mentioned that this particular scenario depends on only one parameter, namely K0 by A0. We'll work with certain value for this K0 by A0, which is of the order of 10 power minus 8, which will become clear. The reason for this choice will become clear as we go along. And what is the tensor power spectrum? As you can imagine, in a Matterbound, the tensor power spectrum is strictly scale invariant. I had already argued as to why you can, you will expect to have a scale invariant spectrum prior to the bounds on scales of cosmological interest, post bounds as well. Okay, as illustrated in this plot, we have been able to establish this both numerically as well as analytically. Now we need to construct a scalar field model to drive the bounds. I had already mentioned as to how the Matterbounds can be achieved with the help of two fluids. One which behaves like matter, and the matter component we model with a canonical scalar field. It is well known that if you have matter, you need pressure equal to 0. You cannot do without a potential. So we consider a canonical scalar field with a specific choice of the potential, and then you have, to describe the matter component, okay, or rather the component which behaves like dust, and we choose to work with a non-canonical scalar field and a ghost field to drive the to mimic the radiation, and one can work through the background equations and show a potential of this form where you have a 1 over cos hyperbolic power 6 potential, which can lead to the scale factor as written down on top. What one finds is that you would have heard that the unit is expanding. In contrast, during contraction, a field will rise in the potential. So imagine you have a 1 over cos hyperbolic power 6 potential. Prior to the bounds, the field rises up, reaches form of the potential, and once it reaches it has in the universe as essentially down the potential. So you have two fields here, right? And as is well known, if you have two fields apart from the curvature perturbation, you have isocurvature perturbation as well. So you need standard things, and you can construct two quantities which are gauge invariant. The scalar perturbation, the curvature perturbation R, which can be expressed as a linear combination of the gauge invariant quantities delta phi and delta chi, and the isocurvature perturbation S. What one finds is that there is a H dot which appears in the denominator in both, poses some difficulty in evolving the perturbations. I will skip for want of time those details, and if there are questions, I can respond to them. What all you need to do is that arrive at equations governing an R and S. This can be easily arrived using the first order Einstein's equations and the equations governing, by perturbing the equations governing the scalar field phi and psi. Or equivalently, you can obtain the corresponding equations for R and S from the conservation of the perturbed energy, stress energy tensors for the two scalar fields. And these equations are given by these. There are some challenges in integrating these equations. I will just proceed to illustrate the results. If you recall, H dot, turned, from negative to positive around the bounds. At these points, we have some S because some of these coefficients diverge, but we are able to work in different gauges and evolve these perturbations without any difficulty. But we will see that R and S will exhibit spikes at certain points where H dot vanishes, as will become clear later. So we have been able to solve these analytically. In fact, I will skip those details and proceed to present the results. And this is the behavior of the curvature perturbation R, the isocurvature perturbation S, and the tensor perturbation, which I've already illustrated earlier. And what I have plotted on the left and the right corresponding to two sufficiently different values of wave numbers to illustrate over a wide range of scales, the curvature perturbation behaves in a very similar fashion. There are a few points that I need to highlight here. Notice post bounds, we have two curves, one which settles down at a higher value, which corresponds to the curvature perturbation, one which settles down at a lower value in red and cyan, which will correspond to the tensor perturbation, and there is a mode which decays post bounds, and that corresponds to the isocurvature perturbation. All these are desirable features. This illustrates the fact that the curvature perturbation has a larger amplitude rather than the tensor perturbation in order to be consistent with the current constraints on the CMB. And the isocurvature perturbation also begins to decay post bounds in order to be consistent with the CMB data. That is, but this is not what happens post bounds is not, doesn't indicate certain things that happens prior to the bounds. What one finds at very early stages, of the bounds, the tensor and the scalar amplitude, which appear here, they appear almost the same here because of the wide range in their amplitude as, one evolves through the bounds. One finds that the tensor to scalar ratio, in fact, is greater than 1 during the contracting phase. This is a very one of the challenges one has to overcome in order to ensure that the curvature perturbations are sufficiently enhanced as they evolve across the bounds, much greater than the tensor perturbation, in order to be consistent with the data post bounds. And this is clear from these two plots here. What has been plotted? I have plotted the blue, which is the curvature perturbation spectrum, green, the isocurvature spectrum, and red, the tensor power spectrum before the bounds in dotted lines and after the bounds in solid lines. Notice the dotted lines. The curvature, isocurvature green is always much smaller than the blue curve, which is good because that can be consistent with the data. But notice prior to the bounds, the red is above the blue line, whereas post bounds, the blue is above the red line. And this is, very clearly illustrated in this picture, where I have plotted the tensor to scalar ratio as a function of time. What one finds is that prior to the bounds, the tensor to scalar ratio is very large, but because of the fact that the curvature perturbation is enhanced, considerably across the bounds, one finds post bounds in this specific model, the tensor to scalar ratio is of the order of 10 power minus 6 or so, and it is indeed consistent with the data. And I should emphasize this, as far as this particular model is concerned, it has only one parameter. This is K0 by A0. If you recall, I had chosen K0 by A0 MPL to be 10 power minus 8 or so. And I had made this choice to ensure that the scalar perturbation post bounds is Kobe normalized. Once you fix that, there is no parameter left, and the tensor to scalar ratio turns out to be 10 power minus 6. Of course, we have strictly scale invariant spectra here. We need to introduce a tilt. I will not spend much time on this because it is fairly easy to achieve. All you need to do is that, remember, we had worked with 1 plus K0 squared, eta squared, 1 plus epsilon. Epsilon was 0 originally. Now I can introduce an epsilon and work with a suitably small epsilon to introduce a sufficiently, small tilt so that I arrive at a scalar spectral index of 0.96 or so, and that can be achieved by this action. You just need to tweak your original action, and you can go ahead and calculate the spectra prior and after the bounds, and it has a small tilt. And as I mentioned, if you work with this epsilon, if you choose an epsilon parameter to be of 10 power minus 2, you can arrive at a spectral tilt of 0.96 or so. So we have been able to arrive at spectra, primordial spectra, that are largely consistent with the CMB data in the context of bounces. But can bounces generate features? And why do we need to consider features? You'll all be familiar with this curve where you have the CMB data and in blue dots, and you have the red line, which corresponds to the spectrum, nearly scale invariant spectrum, corresponding to a spectral index of 0.96 or so. And this nearly scale invariant spectrum without any features fits the data fairly well. However, what one has noticed is that if you introduce certain features in the primordial spectrum, that we can focus on 3 types of features. Notice this red curve here. If you have a sharp drop in power on large scales, and then certain, couple of oscillations before it settles down to a constant value, or you look at this green curve here, which has a couple of oscillations, before it turns scale invariant on either side. Or if you have a set of persistent oscillation, like the blue curve here, which runs over the entire range of scales, one finds that, it improves the fit to the CMB data. In the context of inflation, you can generate, such spectra by introducing corresponding features in the inflationary potential itself. Think of a linear potential. Remove these oscillations in this red line and draw a line through these oscillations. You can have a linear potential. If you have a linear potential, you'll have strictly slow roll inflation. The moment you introduce these oscillations, the field sort of goes up and down this potential, and it introduces tiny oscillations in the background field. In turn, you have some oscillations imprinted on the primordial spectrum. And if you introduce a small step, I don't know whether you're able to notice this small step here in this green curve, which corresponds to an m squared phi squared potential, which has a small step introduced, then you can generate a burst of oscillation like this green curve here. Or you can have a point of inflection. This blue curve is like a phi squared minus phi cube plus phi 4 kind of potential. It contains a point of inflection. What it allows is that it allows you to generate 2 regimes of slow roll inflation with a brief departure from inflation, in the context of generating larger amounts of primordial black holes. What it does is that they generate spectra of this form, like the blue one, the red one, and the green one is not very, the red one contains many oscillations. It is generated by something called the axion monodromy model. The blue one is generated by this model containing points of inflection, and this green one is generated by introducing a step in otherwise smooth inflationary potential. All these turn out to future, if such features are confirmed by CMB and other data, can these be generated in the context of bounces? If they cannot be generated, evidently the bounces can be ruled out. Now the challenge is as follows. We have been discussing, matter bounces. One finds that matter bounces are very unstable, extremely unstable. They need fine-tuned initial conditions for the background. Otherwise, you will not be able to evolve them at all. In other words, they are repellers. We are able to achieve features in the context of inflation. So if you have a linear potential, you have an attractor trajectory, and then if you introduce tiny oscillations, it deviates slightly from this trajectory, but eventually returns to this trajectory. And that's why you're able to generate some, narrow set of features before the spectrum turns scale invariant on the other side. This is not possible if you are not on an attractor and if, on a repeller. And this is the challenge in the context, for generating features, with matter bounces. Therefore, one needs to turn to models that allow stable contraction. And this is where the so-called ekpyrotic scenario comes in. And this is easy to establish. We are going to focus, that is, this ekpyrotic models can lead to stable contraction is easy to establish. We will focus on models where the scale factor is given by A of eta of this form. Notice lambda squared appears in the denominator here. And you can immediately show that this corresponds to an equation of state. Such scale factors correspond to an equation of state for the sources, which is given by this W here. It is lambda squared minus 3 by 3. And it is again easy to show using the equations of the scalar field and the Friedmann equation that such a scale factor can be driven by a potential, by an exponential potential. It is well known that power law inflation, for instance, can be achieved by an exponential potential. In the same manner, power law contraction can also be achieved with an exponential potential. And what one can show is the following, that this V naught is determined, can be written in terms of these parameters A1, eta 1, and lambda. And what one finds is the following. If you are in an expanding universe, the solutions here for the scale factor and the potential, on the scalar field are stable when lambda squared is less than 6. Notice there is a minus sign here. Lambda squared is less than 6 implies that V of phi is positive. So if lambda squared is less than 6 and you are in an expanding universe, the solutions are stable. However, in a contracting universe, the solutions are stable only when lambda squared is greater than 6. Notice what happens when lambda squared is greater than 6. V of phi will contain a coefficient, to the exponential, which is negative. And, another way of saying is that this W squared, when lambda squared is greater than 6, becomes greater than 1. In other words, you have a stiff equation of state. In such a case, goes as 1 over a power 3 into 1 plus W, grows faster, because we are in a 2-2, allows these so-called, these scenarios are called ekpyrotic scenarios. These allows instabilities, which are a bane of many contracting universe models. So this scenario where V of phi is negative, we'll work with lambda squared, greater than 6, is often referred to as the ekpyrotic phase. However, there is a challenge. Such a scenario leads to a very blue curvature perturbation spectrum. We need to turn this blue curvature perturbation to red. That's our first goal. How can we do that? Well, what we do is that we, apart from my original potential V ekpyrotic, which is the exponential, I introduce another field, and I also interchange this potential. I multiply my V ekpyrotic potential with the potential which is given by this here. It depends on phi as well as chi. Chi is my new field. I need to notice that this is a non-canonical field because of this factor e power 2 b phi, and one works with a b of phi which is linear in phi, and one can show the following. While the curvature perturbation spectrum initially turns is blue, what happens is that because of the presence of the second field, notice the form of this VC of phi comma chi. One finds that, as phi approaches phi c, there is a turn that arises in the potential, and this turning, what it does is as follows. This quantity xi here indicates the coupling between the curvature and the isocurvature perturbation during the initial stage. N is E4. This is left large N corresponding to the early stages of contraction. As N decreases, we are approaching the bounds. Okay, we have just used E-folds because this does not correspond to a symmetric matter bounds, and we are not going to evolve the perturbations across the bounds. Our goal is to generate features during the contracting phase. What we are going to, but our challenge prior to that is to generate a red tilted spectrum in an ekpyrotic phase. Recall why we are working with an ekpyrotic phase. It allows a stable contraction. So let me come back to this quantity xi. Xi is indicates the strength of the coupling between the curvature and the isocurvature perturbation. I can by hand forcibly turn the field from moving along the chi directions toward the, from moving along the phi directions toward the chi direction. When I do that, there is suddenly a strong coupling between the isocurvature and the curvature arise. And notice the green curve on the right corresponds to the isocurvature perturbation, while the blue corresponds to the curvature perturbation. As the field turns, what happens is that the curvature perturbations are boosted by the isocurvature, and when the field has completed its turn, one finds that the amplitude of the curvature and the isocurvature perturbations are roughly equal, and one uses this mechanism to convert the strongly blue power spectra that arises in the ekpyrotic scenario to red spectra. And we have illustrated here for two cases. One, we have converted a completely blue spectra here. Notice the spectra here. This is prior to the turn. The green one is the curvature perturbation spectrum. Notice the curvature perturbation spectrum is strictly scale invariant. We have started with two scenarios where I can have a feature. Now remember, since I have an ekpyrotic phase, which is a stable phase, I can introduce features in the potential to generate in the primordial spectrum. We have been as a featureless spectrum, and another spectrum with features. This blue curve is prior to the turn in the field space. This is the ekpyrotic spectrum, which is nearly scale invariant. After the turn in field space, one finds that the blue and the green curve have roughly the same amplitude, and importantly, the curvature perturbation spectrum has turned scale invariant. In fact, red. Okay, and it all is that the features in the eventual perturbation spectrum are essentially the features that arise in the original isocurvature perturbation spectrum. And through this mechanism, we have been able to generate a variety of features. One with a cutoff, one with a couple of bursts of oscillations, and another which continued oscillations over a large range of wave numbers, just as we had in the context of inflation. Many challenges remain. We need to evolve these curvature perturbations across the bounds and eventually compare them with the CMP data. I think I've run out of time to able to discuss 3-point functions in a bouncing universe. So I think I'll just proceed to my summary and outlook. Earlier efforts had suggested that the tensor-to-scale ratio might naturally be large in matter bounces. I'd explained what the reason behind this. Okay, one finds that during the contracting phase, the tensor to scalar ratio is of the order of 20 or so in a Matterbound. We have been able to construct a Matterbound scenario where post-bounds, the tensor to scalar ratio is consistent with the observation. In fact, is incredibly small. If one sees tensor to scalar ratio of 10 power minus 3 or so, this model will be ruled out. Many of the simpler and fine-tuned bouncing models will prove to be unsustainable, like the matter bounces, if future observations, as I mentioned, confirm the presence of features. For the first time, we have been able to construct a bouncing scenario which lead to features that have often been, as I clarified, we have evaluated the spectra prior to the bounce in these ekpyrotic scenarios, affected by the isocurvature perturbation. But we expect that the spectra shape will not change as you evolve them across the bounds. But nevertheless, we have to do that. We are currently working on it. What's the outlook? In inflation, classical perturbations present at early times will decay. In contrast, they can grow strongly during the contracting phase in bouncing models. So such perturbations need to be assumed to be small in very smooth bounces. This statement is particularly true in the context of scenarios such as the matter bounce. This is not such a problem for scenarios such as ekpyrotic bounces, because the background field dominates the evolution during the contraction. It has been argued that due to the growth of the amplitude of the curvature perturbation by sun approaches bounce, quite generically, the scalar non-Gaussianities generated bounces turn out to be large. In fact, there is a no-go theorem which says that it is impossible to have small values for FNL and small values of the tensor to scalar ratio. We are currently examining this in a wide class of bouncing models. And also, after the bounce, the universe needs to be, transited to a radiation-dominated epoch. Such a transition has to be achieved, and we are also examining this mechanism of reheating in these bouncing scenarios. With those remarks, I will stop here. I would just like to point out that these are the three students, who have done the work with me. Ratul Nath Ravindran, whom as I said, was a graduate student at IMSC, working with me, and he's currently a postdoc in Seoul. Devika Chowdhury, who's currently a postdoc at TFR, and Srinath, who was until recently a postdoc at IUCAA and currently a faculty at NIT Surat. Thank you very much for your attention.
Thanks very much, Sriram. I mean, of course, we can't applaud here, but Zoom allows you to applaud if people know how to do it. The way we are going to take questions is that I would ask people to use the option of raising a hand, which you can get in the participant screen at the bottom. Please raise your hand and I'll unmute you and ask you to ask question. Meanwhile, while we are waiting for that, let me also announce that next week we restart our NEEM seminar, and we will send out notices on Tuesday, for example, on next Tuesday at 4 o'clock, like we were doing before the summer school was on. And we have talks lined up for you on Tuesdays as well. Next Thursday, our speaker is Professor Martin Rees, famous cosmologist, ex-president of the Royal Society, and he's going to come on, and we are going to circulate his. This is the colloquium next Thursday. We're going to circulate his topic, etc., very soon to you. I see already Swagat's hand up. Swagat, can you ask your question?
Hi, Sriram.
Hi, Swagat.
So I have several questions. So I'll
Sure.
first ask about tilt. So you showed how to introduce this epsilon parameter kinematically and obtain a scalar tilt as well as tensor tilt, both at a time, right?
Right.
Do you have any consistency relation, let's say, between R and NT in your model, Matterbound model?
This is very much like power law. Yes, there will be.
Uh-huh.
This is very much like power law inflation. So I believe there will be, yes. I'm sorry. No. I stand corrected. I misunderstood your question. No, it is not clear to me whether there will be a relation between R and NT. R seems to be determined by a different set of parameters, and NT seem to be determined by a different set of parameters. And I should also mention one of the challenges may be, that R will depend on completely on the details very close to the bounds, how the curvature perturbations are enhanced, while the tilt itself is determined by the behavior far from the bounds, prior to the bounds. So no, I do not have a consistency relation like one has in the context of inflation. I misunderstood it.
I will wait for my other questions.
Sure.
Okay, thanks, Swagat. The next question up there is somebody called Nikodem Poplovsky. Go ahead, I'm unmuted you.
Oh, thank you. So, in Einstein-Cartan theory of gravity, space-time torsion can naturally provide a bounce in the early universe, and quantum matter production right after the bounce can actually create an inflation, which will eventually stop because torsion eventually gets weaker. My question is, would a scenario in which you have both bounce and inflation be consistent with observations?
I know that there are a set of people who work on such scenarios where there is a bounce, where there is an inflation followed by the bounce. That makes the bounce redundant. Okay, the whole idea was to replace inflation by the bounce to generate the primordial perturbations. If you have both, it makes it redundant, and I can imagine that you can construct scenarios where they are consistent with the data. But unless you have some modes which do not emerge from suborbital scales during inflation, and they have to be generated much prior to that, say in the bouncing contracting phase, I think where all modes, all the perturbations on all scales of interest are generated during inflation, having a bounce as well, it allows you to overcome the big issues with the singularity, but it is not clear whether you need for the generation of perturbations.
Thank you.
I'll come.
So I feel it is not, both are not simultaneously or not required.
Great. Can we'll come back to Swagat. Swagat has hand up, but can Shantanu ask his question first?
Yeah, so maybe I missed this, but do you have reheating in these models, and or how do you transition to, I guess, the radiation-dominated phase? Because that's another big can of worms in inflationary models. So, or there's no reheating.
It's not a big can of worms. You can achieve reheating relatively easily. Perturbative reheating can be easily achieved. All you need to do is that set up a coupling between the scalar field and your other scalar fields, which are supposed to mimic the remaining parts of the standard model. Okay, and you can transfer the energy. You can do that in these models as well. I haven't attempted in greater detail. The challenge is to have well-motivated couplings that can transfer this energy. Transferring energy, whether we are going to do it post-bounce, whether here or in inflation, to another field or another set of fields, which is supposed to mimic the standard model particles, is not challenging. It's not difficult at all. So in that sense, we haven't done it, but I don't think reheating is a major issue.
Thanks, Sriram. Swagat, can you go ahead again?
Yes. So my second question is about a pyrotic scenario.
Mm-hmm.
So in order to generate a red tilt, so when you generated a red tilt for your curvature perturbations, your isocurvature also started growing, right? If I understood correctly.
Yeah, it's a challenge. It's a challenge. So we believe that we haven't completed this. So what we have done is that calculated the spectra prior to the bounce. So I need to evolve the perturbations post bounds in order to check whether the isocurvature eventually comes down. This is proved to be a little tricky to model. We will need yet another field possibly to achieve the bounce. Me and Ratul are working on it, but it is turning out to be a challenge. We believe the isocurvature continues to grow. You are correct. You observed it well. We will need to eventually make it come down. But if you compare the behavior in other models, once expansion sets in, isocurvature comes down. So we are hoping to evolve these models across the bounds and examine the behavior of the isocurvature perturbation. So yes, the model is not complete in that sense.
All right. I have one more question, if I can ask.
It's fine with me.
Yes, go ahead. Go ahead. We have other questions coming up, but go ahead, Swagat.
So this is about non-Gaussian. I think I have asked you before, but somehow I don't remember now. So did you mean that you will get a large scalar non-Gaussianity for sure?
So what has been, okay, let me state where I am confident of. It is easy to calculate the non-Gaussianity during the contracting phase. I know IUCAA, Brandenberger and others have done. What they find is that it turns out to be large. In fact, there are strange contributions and it turns out to be large. The challenge is, what is the contribution across the bounds? I'm not on top of this part, but I know that there has been claims that, as I mentioned towards the end of the talk, that it is difficult to keep both the tensor to scalar ratio and the level of non-Gaussianity small. Having said that, personally, I haven't seen a very satisfactory calculation where all the curvature perturbations are evolved, all the modes are evolved across the bounds, and the non-Gaussianity is calculated completely. I was trying to describe that for the case of tensors, but I ran out of time. That is one case where we have been able to do. We are facing a stiff challenge in doing that for the case of the curvature perturbation because of the modeling involved.
Thanks very much. I mean, the co-hosts cannot raise their hands, so I know Kandu has a question. Kandu, go ahead and ask your question. Unmute yourself.
Thanks, Sriram. A lot of interesting calculations. I was wondering about this whole question of vector perturbations. They were supposed to blow up as you come to the bounds, right? What happens to them?
So, well, I use them to generate magnetic fields.
I know, but they don't blow up or what?
They will not blow up, right? I mean, in the sense of, yes, they will behave in a certain manner. In ekpyrosis, it is fine because, their energy density goes as faster than 1 over a power 6.
Yes.
So unless something goes faster than that, to my knowledge, there is nothing which behaves like that. In fact,
you mean once you have a finite scale factor, they will blow up, but they will decay again, you're saying?
Yes, exactly. And that is in the context of situations like Matterbounds, etc. Yeah. Okay. In these cases, I am of course assuming that they don't play a role at all. Initial conditions
yes.
that they don't play a role. But if reason, because it will dominate everything else during the contracting phase.
Correct.
And it is slow contraction, so it will proceed for a very long time.
Okay, yes. We'll talk later.
Sure.
Thanks very much. I think Swagat has another question. This will be the last one.
Yes, I just wanted to have a take-home message. So it seems that certain observables, to be sure about the prediction of certain observables, we need to really evolve it through the bounds.
Absolutely. Yes. That is not just certain observables. Look, when you compare with the CMB data, right, you assume that, our goal has been as follows: to sort of evolve until the time which would correspond to reheating in the bouncing scenario. Okay, so you need to, so therefore, there are many discussions that take place prior to the bounce. Something like the shape of the spectra will be. Therefore, it is very important to evolve the perturbations across the bounds. There are efforts to evolve perturbations across the bounds, but there are many cases where the perturbations are evolved only prior to the bounds and conclusions are reached. So yes, in order to compare with the CMB data, I have to evolve across the bounds to roughly an epoch, as I said, that corresponds to reheating in the Big Bang scenario.
Thank you, sir.
Thank you.
Great, thanks, Sriram. This was a
Pleasure.
fantastic talk, and applause, and hope to see you soon. Great, thank you very much.
Yeah,
And
hope,
thanks.
as I know, I will try to visit as soon as situation